In my earlier video, I had discussed about pointwise convergence of a sequence of function, and today I will discuss uniform convergence of a sequence of function. At first, just recall what is the pointwise convergence of a sequence of function and what is different between pointwise convergence of a sequence of function and uniform convergence of a sequence of functions. Sequence fn converges pointwise on D to the function f means if for every x belongs to D, the sequence fn converges to fx. And this is true for every x belongs to D. So, here the convergence depends on the point, and epsilon delta definition of pointwise convergence is f1, f2, f3 is pointwise convergent to the function f who is defined from I to R such that for all x belongs to I and for all epsilon greater than 0 there exists a capital N who is depends on both epsilon and x such that for all n greater than equal to capital N, absolute value of fnx minus fx less than epsilon. Notice the capital N depends on both epsilon and points. So this is the pointwise convergence sequence. For this expression, consider this is y equal to fx. This is the fx plus epsilon neighborhood, and this is fx minus epsilon neighborhood. That means this distance be epsilon distance. Okay. Then after some stage all function will be contain this neighborhood. Consider this is actually y equal to gx. Are you getting the method? Oh well. Recall my earlier video. Fnx equal to x over n for all x belongs to R. I had seen Fn convergence pointwise to the function f equal to 0. And this is the picture of x over n. This is f1, this is f2, this is f3. I had seen in my earlier video, I had seen this after some stage, all function tends to fx equal to 0 function. Now, I will say, is this convergence is uniform convergence? Consider this epsilon distance and notice this is true for n equal to 3, and if we take this epsilon distance here, then this would be true for n equal to 4. Are you getting? That means here the capital N depends not only epsilon, this is depends also point. So this convergence is not uniform convergence. Okay? Are you getting the idea? Well, now I will apply the epsilon delta definition of uniform convergence. Fnx equal to x over n, and consider this is uniformly convergent. Okay. For this, consider epsilon equal to 1, then there exists capital K belongs to natural number such that absolute value of x over n less than 1. By definition, this is true for n greater than equal to k and for all x belongs to capital X. This is the definition of uniform convergent, and from this line this implies mod x less than n for all n greater than equal to k and for all x belongs to capital X. But if you choose x equal to 2k, then that implies 2k less than n. And notice here the definition of uniform convergent imply n greater than equal to k. But here I have got 2k less than n. That means this break the definition of uniform convergent. That means our assumption is wrong assumption. This function not uniform convergent. Are you getting? To check uniform convergent, how we have to apply the epsilon delta definition? Okay. Consider one sequence of function fnx equal to x plus 1 over n. Here notice f1x equal to x plus 1, f2x equal to x plus half, f3x equal to x plus 1/3, so on. And when n goes to larger and larger, then this sequence of function actually converts to fx equal to x. That means actually the sequence of function converges pointwise to fx equal to x function. We'll see, is this convergence is uniform convergence? This pointwise obviously. Consider small epsilon and notice here this epsilon distance represent the distance of the function from the limit function. Here notice one thing, this distance be always same. Always I will get one capital N such that distance of fnx minus fx less than epsilon. So this convergent is always uniform convergent. Now I will see other sequence of function fnx equal to 1 over nx, and this is true for x belongs to closed one open infinity. And from the picture it is easily to verify. After some value of capital N, all value goes to 0. That means obviously this function fnx equal to 1 over nx pointwise convergent to 0. Convergent to the function fx equal to 0. This is the function fx equal to 0 line. Let's verify. Is the convergence is uniform convergent? Obviously this function is uniformly convergent to fx equal to 0 function, because notice the graph here. After some stage all value eventually close to 0. So if we take small epsilon distance, notice after some stage all the function will be belongs to this epsilon band. So here all the value actually eventually close to 0. Here the convergence is not depends point. So this convergence is uniform convergent. Are you getting the method? Our next function is fnx equal to x square over n, which is defined for all n belongs to natural number. Obviously this function is look like this parabola type. This is f1x, this is f2, this is f3, so on. And notice here for large value of n, this function actually converts to fx equal to 0 line. That means fnx equal to x square over n is pointwise convergent to the function fx equal to 0 next question, is this convergent is uniformly convergent? Here notice, for large value of n, fnx would be x square over n. Obviously this function be unbounded for any capital N. Are you getting? If you take here any small epsilon neighborhood, since here the all function will look like parabola type, so here the all function does not belongs to this neighborhood. That means this function actually does not convergent. Uniformly. Are you getting? And the mathematical expression of uniform convergence of this function would be, if the function be uniform convergent, then n greater than equal to capital N, absolute value of x square over n minus 0 less than epsilon. And this is true for all x belongs to real number. Now at first just imagine, is this relation here true for all x? Here notice, or here the function is look like parabola type. So did this expression not be true for all x? Because there are some x, because here this is the parabola type, so obviously there is some x. This is more big. Since x is big, so x square over n obviously will be big. So then this expression not be true. Then this expression would be x square over n would be greater than epsilon, which will be break the condition of uniform convergent. So this function not be uniform convergent. Are you getting? Well, if n converges to f uniformly, that imply obviously if n converges to f pointwise, because uniformly convergent is stronger condition, but if n converges to f pointwise, that does not imply if n converges to f uniformly. Okay? Now there exists a nice theorem. Let I subset of R, then a function fn which is defined from I to R is continuous for all n belongs to natural number, and fn is uniformly convergent to the function f, then obviously this f which is defined from I to R is obviously continuous function. Are you getting? Well, that means in pointwise convergent, the continuity of f does not necessary condition, but in uniformly convergent, always f will be continuous. And the proof is very easy. Let's see the proof. Our goal is, we have to prove f is continuous. That means our goal is, for all epsilon greater than 0, we have to find there exists delta such that absolute value of x minus x naught less than delta imply absolute value of fx minus fx naught less than epsilon. This is our goal because we have to prove f is continuous. And since here each fn is uniformly continuous, that means obviously fn is continuous and fn converges to f uniformly means let epsilon greater than 0, then there exists capital N belongs to natural number such that absolute value of fn x minus fx less than epsilon over 3. Since the function is uniform continuous, that means after the stage capital N, all the function belongs to the neighborhood of f. And since each fn is continuous, that means there exists delta greater than 0 if x minus x naught less than delta, that x naught here the point in the function fn. The graph is look like the fn function and this is the point x naught. That implies absolute value of fn x minus fn x naught less than epsilon over 3. And since our goal is we have to prove for all epsilon greater than 0 there exists delta such that x minus x naught less than delta imply fx minus fx naught less than epsilon. Here notice in my hand has two conditions. Therefore, we can write absolute value of fx minus fx naught as fx minus fnx plus fnx minus fnx naught plus fnx naught minus fx naught. Okay? And by triangle inequality, this is true. fx minus fnx plus fnx minus fnx naught plus fnx naught minus fx naught. Okay? By this, since this is less than epsilon over 3, that means obviously this part less than epsilon over 3, and since I have got this is less than epsilon over 3, that means this is less than epsilon over 3 plus similarly this would be less than epsilon over 3. That means this is equal to epsilon over 3 times 3, that means this is equal to epsilon. Are you getting the relation? That means absolute value of fx minus fx naught less than equal to epsilon. That means our proof has done. Now I will see other example. In my earlier video, such fnx which is defined 0 for minus infinity to close 0, nx for 0 to 1 over n and 1 for x greater than equal to 1 over n. This sequence of function I had seen converges to a pointwise, and the point is fx would be 0 for x less than equal to 0 and 1 for x greater than 0. And obviously, since f not continuous here, so by previous theorem we can tell easily the function not uniform convergent. Okay? Are you getting why this theorem is very important? Since our aim is not depend only theorem, so try to prove this math why this is not uniform convergent. I will approach this math by epsilon delta definition of uniform continuity. At first consider this fn be uniform convergent. For this, consider epsilon equal to half. Then there exists capital K belongs to natural number such that by the property of uniform continuity, since I have considered the function is uniform continuous, for all x belongs to capital X, absolute value of fnx minus fx less than half and this is true for all n greater than equal to k. So, in particular, since this is true, this condition is true for all n greater than equal to k, so in particular, absolute value of fkx minus fx would be less than half, and this is also true for n greater than equal to k. Are you getting? Because I have considered this relation because this is true for all n greater than equal to k. Now take x equal to 1 over 2k. Then obviously x lies between in the interval open 0 to open 1, and in the interval notice the value of the function is 1. So here the fx equal to 1. Since I have considered this particular x, so in the interval 0 to 1 over k, the value of fkx would be k times x, then this value would be half. Put the value in the relation, absolute value of fkx minus fx would be here fkx equal to half, and I have seen fx equal to 1 in the interval, so put the value, then this value would be half. Therefore, our assumption is a wrong assumption. I have considered absolute value of fnx minus fx less than half for all n greater than equal to k if the function be uniform convergent. But here I have got this part. So fn does not converges uniformly. Are you getting? Oh well. Today I will stop here. In my next video, I will discuss this topic elaborately, because this topic is very important for any competitive exam. Thank you so much. See you soon. Stay safe and stay positive always.